Good evening, friends. My name is Mikhail Kiselev. I am in charge of a Neuromorph lab at Chuvash University. Together with my colleague Denis Larionov from Tifrum, which is a Rosatom subsidiary, we would like to make a presentation on Neuromorph AI systems. We all have seen the success of AI technology. It's everywhere. AI addresses very scalable tasks. This is definitely great progress. But at the same time, we see the new challenges that stand in the way of further development and that really slow us down. There are several types of problems. Some of them are purely theoretical. For example, we are not fully understanding some cognitive processes, memory, goal setting. The theory is far from being complete. But there are other types of problems. They are in the engineering domain. They have to do with energy consumption. If we look at biological systems, living systems like human brain or animal brain, it is obvious that the neuron systems are huge. A human brain has dozens of billions of neurons, 10 to the 14th degree. This is a huge system, but it uses very little power, just only about 30 watts. If we extrapolate this system, if we were to create an artificial system using today's hardware, we are going to need about a gigawatt of power. With this kind of energy, if we were to squeeze it into a human head, it would explode like a bomb. So that's the big difference between natural intelligence and artificial intelligence, and that's a big slowdown factor. Some time ago, we have heard the concept of neuron networks that can address this problem in the same fashion as the problem is handled in nature. Why a human brain is so energy efficient? The communication between neurons and human brain is different from what happens in traditional neuron networks. In the brain, neurons would send short pulses, and the connection between neurons is not using any power until a spike is sent through the system. And once it's through, then nothing is happening again. This is the principle that has been used in the third generation neuron networks, that is spiking neural networks. The neurons are not exchanging numbers, they are exchanging events, spikes. We call them spikes. A neuron would receive a spike, it would handle a spike with some small, short operations, then there is no computing and it does not use any power. So this is a spike model that explains the high energy efficiency. But there are other benefits as well. For example, this solution is very sustainable and it's very highly resistant to noises. It's resistant to any kind of interference, which is a problem for all other systems. A brain is a set of asynchronously working simple devices. There is no synchronizing signal. If we want to create very big models, very large neuron networks, this turns into a huge benefit. A huge number of neurons do not require any synchronization. In SNN, time of impulse traveling from one neuron to another is very important. It does not happen instantaneously. And a spiking neural network becomes a non-linear system. Such system becomes a versatile computing system, which can process non-static data, but rather flows of multimodal data. That is very useful in robotics and in several other fields. A short time ago, these models of spiking neural networks have become used in the practical field. The first neuron processors have been created with that purpose. Professor True North, processor True North was created by IBM, and it had very high level of performance. One silicon could support 1 million neurons with 256 million connections. This chip was made for the military, and that's where it will be used most of the time. The export of this technology to Russia and China is prohibited. Intel was the next corporation that made the next step. They built Intel Loihe. It was different from IBM True North. This chip supported the function of learning. In True North, neurons were static. They were not trainable. In Loihe, we have a dynamic system, which is the basis for a neuron network training. The third neurochip was created in Russia by Matit. The product was named Altai. It is similar to True North with less performance, but it has a number of benefits as well. So this is a local development. This chip, just like True North, has some serious constraints. It is not trainable at the chip level. For a neural network to be able to process practical tasks, it needs to be trained with use of traditional systems, usually GPUs or GPU clusters. So there's got to be a system that can train a neural network. And then it would be applied to this chip that will do the practical execution. So the main benefit is low power consumption. Now I'm going to pass the floor over to Denis Larionov, and he will tell you the rest of the story. Denis, it's all yours now. Good evening, colleagues. I work for AI Lab at Cifrum. We are a Rosatom subsidiary. Let me tell you immediately that the response to the technical challenge that we have, that is the training function, is the project that we had to create a self-learning system, neuromorphic in nature. We are talking about the hardware part and an ecosystem of software built for it. We're talking about high-level components, frameworks for some tasks that can be done in the way of Python libraries. We are now in phase 1. We are still facing some unresolved problems in the field of neuromorphic networks. We see that True North and Loihi projects were successful. Therefore, we believe that all the problems will be addressed and taken out of the way. Chuvash State University participates in our work in the field of neuromorphic computing. Motiv is another organization. They are a developer of the Altai silicon, and they have also contributed to the development of hardware and software supporting this silicon. Cifrom is another Rosatom company that is taking care of various digital tasks. They do a lot of development. They create a lot of products, which they also test before they are put in production. We want to create a product, a neuromorphic chip. We want to create high-level tools for specific tasks. Right now, we aim to provide our solutions to the nuclear industry, but that is not the only industry where our technology can be usable. The training and learning function is not essential everywhere. In some areas, it is quite redundant because it makes the hardware architecture of the neuromorphic chip more complex, which has certain costs.
Such tasks can be executed on the Altai CPU, for instance, and I would like to give you a few examples. First of all is portable sensors. Portable mobile sensors that you attach to your helmet or install into a stationary camera. And this is functioning regardless of any server involved. So they can do the object classification, recognition, tracking, and they can recognize the sounds, or like Michael was talking earlier, even odor. And having no bulky power sources make these sensors very, very prospective and very lucrative. The second thing is creation of the principally different systems based upon visual sensors. For example, dynamic vision sensor without any active light, backup light involved. The third one would be improving the intellectual capability of a device. It could be a robot agent that functions in extreme missions in the Arctic, for example, or in the open space somewhere in deep mines, where these efficiency and self-sufficiency become crucial. Using the neuromorphic chip for learning will open new horizons, and as we see it, it will give a huge impact to the development of the entire industry of the artificial intelligence. The tasks that will become resolvable are as follows. So first of all is the hydrophysical and biological systems having an ability to implement the chips in the biosystems, and we can partially or completely recover vision and tactile senses to human beings, and even hearing. And new capabilities are even interesting to open, like we have all read in the science fiction literature. And second sphere is the predictive analytics with big data flows for looking for abnormalities. That's utilized for safety and security. That's what Kaspersky Labs actually do. We work with big scale solutions like, for example, in production in a big facility, and other systems that tackle big streams of data, especially where this data is in huge multitudes, and also the self-learning controllers of robots and bots, robots, agents that operate in very, very changeable environments. Here we're not just speaking about inheritance of the experience of the past, but actually learning the skill completely by interacting with the environment itself. And in the end of this presentation, I would like to point out that the neuromorphic systems and the artificial intelligence topic is very prospective, is very important, and is of a strategical meaning. Thus, it requires joining various competence centers where we can test and evaluate everything. Would be delighted with you joining us for partnership, and we'll be open for your questions. Thank you very much.